So hello everyone. Welcome to our final presentation. So we're Team Stargate and we're trying to improve performance and functionality of Cassandra with a new key value API and in-memory cache. So NoSQL databases are non-relational databases that can help us to handle unstructured and semi-structured data. So compared to the traditional relational databases, they are more flexible and they have better scalability. So one very good example of NoSQL database will be Apache Cassandra. So Cassandra is a wide column store distributed NoSQL database management system. And also it has a masterless ring cluster that can allow us for linear scalability and also data replication. So it has some advantages of high availability, scalability, and fault tolerance. So Stargate is an open source data API gateway for Apache Cassandra, and there are two different types of node. So the first one is the Stargate coordinator nodes, which are responsible for computation. And the second one is the Cassandra node, which is responsible for storage. So we have different methods to interact with Cassandra. That includes Cassandra query language, gRPC, or like HTTP. So we have mentioned a couple of advantages for Cassandra, but Cassandra has its limitations. So basically, it is not friendly for quick catching or to manage the lightweight session data. So that is because Cassandra query language is optimized for large data sets. And also we know Cassandra has some overheads for synchronization and consistency. So that might somehow decrease some kind of performance. So our proposed solution is to build a new key value API as a microservice architecture, which can make our whole system more flexible and have better scalability. And we have in-memory cache with different eviction policy like FIFO, like LRU, to improve the overall performance. And we have a couple of scientific hypotheses, but the main idea is the key value store API we built will be able to help us to handle lightweight session data, and it can some kind of increase the performance of our API. So the major features will be like the key value API. So the key value API will allow users to store data and retrieve data using the key value pair. And also the microservice architecture, which can help us to have better flexibility and scalability, and cache, which can improve our overall performance. And in distributed architecture, we can distribute the load into different nodes, which can have some kind of load balancing and have better cache hit rate. So the intended users of our system will be users who are interested to interact with Cassandra using the key value store API. As for the non-functional requirements, we mainly focus on scalability, which is to make our system distributed. And the second thing will be to have to maintain our system. So we have like code with proper documentation and also some comments to help others in future enhancements.
Okay. Yeah. So for the resources required for this project, since we're building a new key value API for Stargate, we will need some modularity support code in Stargate to connect to the backend service, and also use Cassandra as the database. We'll use Docker to host our microservice on AWS and NoSQL benchmark to test the performance. Micrometer is also used as a monitoring service for different real-time metrics. We would like to talk more about the NoSQL benchmark and micrometers here. So NoSQL Bench B5 is a versatile benchmarking tool for NoSQL database. It can carry out many customized scalable tests with authentication support. We heavily utilize it to do workload tests and analysis. Micrometers are monitoring tool and also measures collection library for JVM-based applications. We use it to collect cache hit rates, latency, hardware usage, efficiency stuff in real time. Here's a brief overview of our system. So we have an API entry point that allows put, get, delete to the database. An authentication process is carried out to prevent invalid access. We need to ensure value persistency and integrity for the database service and use other techniques like caching to boost the performance. Our API service will rely on gRPC client to communicate with coordinator node and Cassandra node and receive HTTP requests from client. Inside of our API service, when a user sends an HTTP request to our service, the request will first go through the request parser, which extract the relevant information such as the requested key and operation. Next, it will be checked in our in-memory hash table. If cache hits, the corresponding value can just be directly returned to the user. If cache miss, it will then handled by a specific handler component, which communicates with the Stargate coordinator node to access the persistent storage. We provide multiple CRUD operations for the systems, like creating, deleting the database and tables. 200 is a success code, and if there are any resource unavailable issues or duplicate tables or databases, there will be 400 and 500 HTTP status code returned. These are similar CRUD operations for the key value pair inside the database. We also got a few cache-related operations to reset cache and or get a cache status. For the cache resetting, we can also reset cache eviction policy and the size of the cache. The cache status can contain the hit ratio, miss ratio, cache size, etc. Here's an overview of the exception status of the HTTP response. The first one is when you did not provide it with a valid token for the access authentication, it will return with a status code of 401. And when you want to add something like a key to the database, but that identifier already exists, it would be a 409 conflicting error. When you are making a call but did not provide the required parameters to it, it will return with a response 400, saying the request is badly formatted. All of these errors are captured and returned with self-configured message without complicated stack traces. Now we talk about the cache slot design. Each of them consists of key, value, key space, table, value type, etc. And hash value is computed with the combination of key, key space, and table. Since we can have multiple same keys in the different database, we support different value types like int, float, and set. We also keep one copy of the hash value inside the cache slots in case there are any hash collisions, so that two of the keys can map to the same cache slots. We design our cache as a list of pre-allocated cache slots. These are initialized at the start of the service and use up 80% of the free memory. We use fine-grained logs, so each cache entry has a related log linked to it. We use hash to index map to get the correct cache slots to read and modify. And free queue is just a queue to store all available cache slots. For the eviction policy, we have three choices. All of them are thread safe based on some Java structures. So the FIFO order is maintained by the concurrent linked queue, which is similar to a normal queue, just it can secure multi-thread operations. The RRU order is maintained by the linked hash map, which is like a double linked list in our usage. We disable its automatic resizing and else entry removal features because those stuff are managed by our other data structures. And we only store and focus on the keys inside the linked hash map. The last eviction policy is a random eviction, and we just use a randint function to generate the right one to evict. Since our design is for light session data, which is a heavy read situation, so we would always update the data to backend Cassandra when doing any write or update operations. Only when reading the data inside the cache can we not reach back to Cassandra. This way, we can ensure a high data consistency level. And for our distributed design, here we use the consistent hashing mechanism to hash multiple servers onto a ring. We use the Java master node for the coordination. The advantage of using this approach is that any of the keys will now only go to one single server. So we do not need to redistribute the key to let it processed by other servers. And there will not be any cache inconsistency issues. Any of the keys would be cached inside the same server.
So now we have talked about the design of our project. Let's talk about how we should test it. So we mostly have two approaches to test this project. The first is a manual approach, and it's pretty simple just to test the error handling and how the accuracy works. We're just calling HTTP APIs on our endpoints. And the second is also our real workhorse, the performance testing, where we leverage the NoSQL benchmark framework, and we use mostly two data sets here. The first is a random data set that is provided by default by NoSQL bench. And the other one is the one we found online real world data sets. And let's go into more detail. So the reason we choose to use NoSQL benchmark is here. The first is very simple to use. All you need to work with is a simple YAML file, and you can define various kinds of scenarios here. And as you can see on the picture on the top, you can define various scenarios. We have the schema and the mean scenarios here. And the second reason is it provides a very nice bindings feature because our implementation requires the authentication token, and the NoSQL benchmark will generate this token dynamically for us. It's very easy to use. And the final reason is users can easily define different kinds of parameters here. Like here, we define the number of cycles, threads, the key range, and rewrite ratio. So we can from different kinds of testing with just minimum change to the YAML file. And here is basically a high-level overview of our testing specifications. So our implementation supports for eviction policies and basically the no cache, the FIFO, LRU, and the random cache. The default number of cycles, so it's just namely the number of GET or pull requests we perform from the client in total is 100,000. And the key range we use is a uniform distribution, and you can also view it as a random distribution from 0 to 1,500. And the default number of slots in our cache implementation is 1,000. The rewrite ratio is 9 to 1. So we just focus on the read-heavy scenarios by default. Our clients test both the single threading and the multi-threading scenarios. And to test how our implementation scales in the real world, we also test both the single node and the distributed scenarios. And here are the metrics we use in our performance evaluation. So basically, we focus on 4 metrics here. The first one is the throughput, and it's very easy to see. It's just the number of requests we process per second. And this is measured by the NoSQL benchmark on the client side. And the second one we see is the latency. So as people have mentioned before, it's tracked by the Java micrometer. So this is something we track on the server side. It's just the time we take to process a single GET, put, or update request. And the third one is cache hit rate, and it's just for us to try to find out how our cache performs under different scenarios, so using different eviction policies. And this is also tracked on the server side using the macrometer. And the final one we had here is testing context. So this is just for the scalability to see how the single node and the distributed implementations work differently. And this is just some more in detail of our test machine. So I won't go into all details here, but something to notice here, we use a T3.xlarge AWS EC2 machine. It has 16 gigabytes of memory, and using a Java 17 JVM environment with a peak number of threads of 61. And so let me first talk about the testing we did before the midterm. So this is the real world data set. And this is data set we find online, but later we found that this data is not meaningful. And I will talk about the reason why later. But you can see here it has 3 main categories. The first is the mapping from the ID to the hashtag. And it's basically each row is mapped from the Twitter ID to the Twitter hashtag. So, but because the Twitter ID doesn't really mean anything to us because there's no duplicates at all, so we just use a Twitter hashtag as the key in our testing. And the second one is map from the users to the number of followers this user has. And same as before, we also use the number of followers as a key because the user ID is also not that insightful. And the final category we have here is the map from the Twitter ID to the geolocation coordinates. And same before, we use the coordinates as the key. And here is the result we get. And so something to notice here is the user followers scenarios is not that insightful because we later realized the number of followers contains little duplicates. So it doesn't really simulate the real world scenario well. But you can see for the ID hashtag and the ID geo coordinates, it actually contains lots of duplicates in its key range. And although it's worth investigating for us to see how this distribution of the duplicates are, but you can see the number of operations per second, the throughput is pretty much the same. The hit rate has a pretty big difference. And we believe the reason is the hashtag might contain a lot more different duplicates than the ID geolocation data set. So that's pretty much everything before the midterm testing. And after the midterm, we did a significant change to our testing scenario.
So there are several changes to our previous deliverables. So first, we added an extra cache eviction policy, which is the random eviction policy as the baseline with cache. And then second, we add more metrics for performance analysis, such as the latency and the cache hit rate, as mentioned above. And then third, we merged different cache implementation branches into the same one to make the test environment more consistent. And fourth, we reran the midterm test and designed more visualizations for evaluation. And finally, we made changes to the distributed architecture of the system because of time limitations. So let's evaluate the performance of our key value API using random data sets in a single node setting. So first, we compare the throughput between multi-threading and single threading. All three cache designs shows a 2.5 times speed up compared to the single threaded implementation. As mentioned earlier, we use an EC2 with 4 virtual CPUs. And the result aligns with the performance change of the baseline without a cache, which means our cache design can effectively support multi-threading. And then let's look at the comparisons between different cache policies. So we can focus on the right part of this figure, which is the multi-threaded scenario. All three different cache designs shows about 1.3 times speed up over the baseline without cache. And the three different cache designs shows similar result in terms of throughput as we use random data sets, so we don't expect the throughput would be much different from others. We also compares the throughput across different write-to-read ratios. So for the baseline implementation, which is the blue line, it performs slightly better when there are more reads than writes. And our cache designs are optimized for reads. So all three cache designs are faster in a read-heavy scenario. And it's worth noting that as the write-to-read ratio increases from 1 to 9 to 1 to 99, there's a decrease in throughput. We think it's because the write operations are too rare, leading to more cache misses. And in this figure, we compare the throughput across different number of cycles. All implementations performs better as the number of cycles increases. Because of the code miss in the cache at the start, when number of cycles is too small, the cache utilization is limited. So the throughput stabilizes after reaching 100,000 cycles. In this figure, we compare the cache hit rate across different number of cycles. And just like the previous one, the cache hit rate increases as the number of cycles increases due to the code miss of the cache. And lastly, we compare the latency across various sizes of the key range. The key range are from 1,000 to 2,000. And a smaller key range results in fewer cache misses as we can expect it, which leads to a lower latency. So as shown in the figure, the latency is directly proportional to the cache miss rate.
So this is the result of the average cache hit rate with the distributed system design compared to the single machine design. As cycle numbers gets bigger, it's clear to see that the distributed system design's hit rate beats the single machine's design. And this is the throughput performance evaluation of the distributed design. Well, the performance trend follows the same as a single machine where LRU beats FIFO, beats random, and all of the cache eviction policy beats the no cache scenario. Well, although the hit rates results comply with our expectations, the performance of the distributed design is actually worse than the single machine. So we suspect that a couple of reasons come into play in this case. First, since all the requests go to the same master server, there is an overhead caused by the master server receiving the request, forwarding the request, receiving the response, and forwarding the responses back. Secondly, we are running both the single machine key value store and the distributed server key value store on the same type of machine. Here, we use Docker to simulate 4 different containers for the distributed settings. This means that 4 containers use the same resources as a single key value store, causing the individual container to use less resources during the experiments. This guess was confirmed with the peak number of threads for the JVMs. As we can see for the single key value store, average of 61 number of threads are used during peak times, while for the distributed design, each machine only gets an average of about 31 number of threads during the peak time.
So in our performance test, we observed some interesting observations. First, multi-threading has constantly outperformed our single-thread version, obviously. But because of some large overhead mentioned before, our distributed approach doesn't work as good as single machine version. And second, our data ranks throughput from different caching policies. In both the single machine case and distributed case, LRU visits maybe intelligent prediction of data access patterns, and maybe it's better use Java's building optimized data structures, has proved to be the most efficient one, followed by FIFO, random, and lastly, no cache version. And third, as we increased the read-write ratio, we saw a corresponding increase in the throughput. This is because write definitely needs a network I/O, while the read only need one network I/O when there's a cache miss. And last observation is talking about the relationship between the hit rate and throughput. Supported by the graphs above, we can see that in both graphs displayed, we use the cycles as the independent variables. And the top graph presents the throughput as a dependent variable, while the bottom graph focuses on the cache hit rate. And as you see, the various colored lines represent different eviction policies. We can observe that both throughput and hit rate follow the previously established pattern of LRU, better than FIFO, better than random. And additionally, the trends of the throughput and the hit rate curves are really similar. We noticed that the 100,000 cycle mark highlighted as a blue line serve as an elbow point for the lines in both graphs. So these observations, especially the last one, lead us to the conclusion that enhancing hit rates should be really crucial for performance optimization in our service. So in conclusion, our analysis confirmed that hit rate is really critically impacts our system performance, especially in throughput and latency. Comparing with other eviction policies, the standout performance of LRU with a high hit rate show that hit rate can consistently lead to great throughput and latency. So maybe for further enhance performance, a good way is to center on enhancing hit rate. This include possibly expanding the cache size to better utilize the node's memory, and maybe adopting two-level caching in single nodes, and optimize our distributed version to overcome the overhead, and maybe explore some eviction policies more closely aligned with user behaviors to also improve the hit rate. So in reflecting on our overall project, a few key lessons stand out, like we need to integrate testing in our early stage. If we can incorporate tests easier in our project life cycle, maybe we can preempt some significant issues and ensure smoother progress later on. We also learned the value of continuous feedback with some like iterative testing approach, and maybe allow us to respond to the different challenges swiftly. And lastly, it's very important for data-driven improvement and feedback informed from our strategies leading up to better outcomes. This is the overall plan. We everything goes really smoothly in the semester. This is a reference terminology. And at the end, we want to express our sincere thankfulness to our mentor, Cassarian and Jeff, for their guidance and support throughout our journey, and also for all the professors and TAs. Thank you so much.
Great job, guys. I have a couple of questions for you. But before I start, I wanted to ask Jeff and Kathy Resson whether they have any comments or questions for you guys. Hey, Jeff, you're on mute.
Yeah, I I was going to defer to Kathir. Do you have any questions?
I mean, we have been catching up weekly, and we went through, the status of each milestone actually. And I don't have any questions at this point. And it's a great team, and we, made a lot of progress in short time.
Great, thank you.
Yeah.
Jeff, anything you want to add?
I was going to ask if there were any things that you would like to see improved in Stargate or any of the other dependencies. Do you have feedback on, hey, this project would have been easier if?
It's hard to understand. It's hard to answer. Because we explore what's the next, maybe next plan, next direction, step by step in the overall process. And I think it's we learn a lot in this process, and because our final design is really different from the really beginning plan, right? And finally, we still in the final version, yeah, we learn a lot in this process. So
Right, but I think the question isn't whether you learned a lot. The question is whether there are any aspects of the Stargate design which could be changed in order to make it easier to implement a cache like you implemented. So think for a moment. So if you were in charge, and you could refactor the Stargate code base to make it easier to do this kind of add-on implementation. Are there any specific things you can think of?
One thing I think is if there's a more detailed documentation, will make it really easier to get our hand dirty at our first semester, because we done most of our job in the second semester, and it's a little bit schedule is a little bit tight.
Okay.
That's really good
Jeff,
feedback.
go ahead.
That's very good feedback. I think how most of the documentation focus is on the surface area of the project, which is the other APIs. You, in building a new API, probably would have benefited from a developer, here's how to build a new API sort of guide. So that's great feedback.
Okay, any other questions from our visitors?
I'm good.
All right, let me ask a couple of questions here. Okay, so I think, turn this off here for a second. So it's, obvious that, we would expect, a cache to improve performance in read-heavy scenarios. And I think you guys did a nice job of doing some bracketing tests to sort of get some numbers there to show that. But you started out with a strong statement, which is that your goal is faster access compared to CQL. And I immediately wrote down, but under what conditions? Okay, so it's clear that it's read-heavy scenarios. But I guess what I'm wondering now that you've shown, that your cache really does improve performance in certain situations, and that there are benefits to deploying a distributed cache. Let's say that I'm a user and now I want to decide whether or not to use the cache. Do you think you could have an automatic setting for everybody that wouldn't really get in the way and then help when there's read-heavy use? Or do you think that I would have to literally sample my typical workload and then do some analysis on sort of how to get the optimal, hit rate in the cache, what the right eviction policy should be, and overall, whether to use the cache or not. So let's say this is successful. Now, how do we make it easy for users to decide whether to use it and then how to configure it? Do you have any ideas about that?
So we actually do currently have an API where users are able to change their eviction policy. Second, they are able to see like the hit rates and the statistics of their current workload. So although there are no like automatic methods right now, the users are able to get some sense of what the hit rates of their current cache is with their current cache policy. But if we want to change this to a more automatic methods, I would imagine that there would be more perhaps a background process that's included to like see how the statistics are changing from time to time.
I see. So you'd have to essentially be monitoring in real time using the scripts that you've already developed essentially, but then have some logic that would detect that maybe you might make a switch. How hard would it be to change the eviction policy on a running instance cache? Is that easy to do, or would you have to shut it down and start it back up again?
Currently, it's pretty easy. It's just an API call, and we automatically clear the cache, basically. Yeah.
Okay. So we would clear the cache, start over again. Okay. So that would be sort of the cost of switching policies, but presumably we would only do this in a scenario where we felt it was worth it to do that. So the sort of margin is different. Okay. So, you concluded that LRU was kind of the best, right? So maybe what I'm saying doesn't mean anything because LRU is really the only cache eviction policy that helps. I can imagine scenarios where LRU would be suboptimal, but what do you guys think? Because you looked at a lot more data sets than I did. So do you think you should just set it and forget it? Or do you think it's worth having those options for developers to explore?
Because we in our code base we use concurrent hash map for LRU, and we in our baseline, like random, we use a really simple array with some manually managed log on it. So maybe this possibly make it not perform as good as LRU in random test case. So I still think we should preserve the switching API for different eviction policies, and maybe we can automatic switch different eviction policies when we monitor that the latency of a single call is larger than maybe 100 milliseconds. We try to use some statistic to switch to a better one. That would be great, maybe.
Okay, so I think what you're telling me is that you don't really feel like the implementation of the policies other than LRU is really kind of optimized yet, so that we would have to do that and then do more testing, maybe to decide if there's one clear winner.
Yes, that's one possible point. And
Mhm.
actually, the data set patterns also is bad. Oh, you're also good at that.
Right. Great. Because when I think about this, I think about applications that store a bunch of data and then constantly refer to it. But basically at the end of a long run, you're going back to, refer to something. So I can imagine cases where LRU, might cause you to constantly have to, refresh, certain values. Okay. So you made a point in your reflection that you wish you had incorporated testing early in your project, right? So of course, what am I imagining? That there must have been some specific issues that came up, right? So what actually did happen that made you feel like you should have done testing earlier?
I can talk about that. So for the distributed settings, we implemented a constant hashing that's designed for a complex workload. So it's assuming that the key value it's getting is from a diverse range of values. But for our testing data set, it's actually just numbers. So that's causing all the requests to go to the same server instead of being distributed across different ones. So we actually kind of have to change that to cater to our benchmark test case in the end. If we knew about that in the beginning, perhaps the testing would be a little bit different when we proceeded with that.
Okay, so there was an assumption that you made about the behavior of the hashing function, which you didn't actually test independently. Is that a good way of describing it?
Well, yes, we we did test it on our assumed data, but we didn't actually test it on our ending benchmark data set.
I see. So it was more the assumption that sort of the distribution of inputs would be the same in the other data sets.
Yeah, well,
Okay.
it's not.
So maybe a good thing to do would be so it's not really writing a unit test, for the hashing function. It's more doing a data analysis of what kind of hash keys would be produced across different data sets, and then, looking at hit rates and so on that way. Okay. I get it. Let's see if I have any other questions here. So if you could add some more data sets, how would you characterize the kind of data sets that you think you should be testing on next? Maybe you know some specific ones that you didn't get a chance to try out, or maybe you can kind of characterize them in terms of what properties you would like them to have so that they give maybe more, diverse testing to your system. Do you have any ideas?
One data set we might test on is like the one you referred before, like maybe use something referring to the previous access. I think the problem is like first we didn't really find a real world good data set, like the problem I mentioned in the presentation, and the second is the NoSQL benchmark has limited documentation support on the real world testing scenario. So yeah, I think that might be something we might look into.
Interesting. Okay. All right. Well, I don't have any more questions. You guys did a great job. Great presentation. Thank you very much. And thank you, Jeff and Kati, for all of your guidance here. Clearly, the team covered a lot of ground and learned a lot from this project.
Sure. Thank you.
Yeah, we were happy to be involved.